Every single second, the space between galaxies grows by thousands of kilometers. Not because they're moving, because space itself is stretching. Right now, while you're watching this, a galaxy 100 million light-years away just got 2,000 kilometers farther from us. And it's accelerating. Here's what nobody tells you about cosmic expansion. It's not slowing down. For decades, scientists assumed gravity would eventually break the universe's growth, maybe even reverse it. Then in 1998, astronomers discovered something that shouldn't be possible. The expansion wasn't decelerating, it was speeding up. Faster every year, faster every second. Something invisible, something we call dark energy, is pushing the entire cosmos apart with a force that grows stronger as the universe expands. It makes up 68% of everything that exists, and there is absolutely no way to stop it. Not with gravity, not with technology, not with any force known to physics. The universe is accelerating toward a future where every galaxy becomes unreachable, where darkness swallows everything, and where even the evidence that the cosmos was ever connected will be erased forever. Tonight we're going to understand why nothing, absolutely nothing, can stop this. Chapter 1. True expansion. When most people hear that the universe is expanding, they picture something like an explosion, a blast of matter flying outward from some central point, like shrapnel from a bomb spreading through empty space. This mental model seems intuitive. It matches our everyday experience of things that expand or scatter, but it's completely, fundamentally wrong in a way that reveals just how alien the actual mechanism of cosmic expansion truly is. The universe isn't expanding into anything. There is no outside the universe, no pre-existing space that the cosmos is growing into. Space itself is expanding. Every point in space is getting farther from every other point, not because galaxies are moving through space like ships through an ocean, but because the space between them is literally increasing. Imagine you're an ant on the surface of a balloon and someone starts inflating it. You're not moving across the balloon's surface. The surface itself is stretching, carrying you along with it. The balloon has no center on its surface. Every point is equivalent. Every point is moving away from every other point. That's cosmic expansion. This distinction matters profoundly. If galaxies were simply moving through space, we could apply ordinary concepts of motion, velocity, and inertia. We could imagine catching up to them, calculating their trajectories, understanding their movement through conventional physics. But because space itself is expanding, galaxies aren't really moving at all in the traditional sense. They're essentially stationary in their local region of space-time, but the space-time between them is stretching like a rubber band being pulled at both ends. Edwin Hubble discovered this in 1929 through painstaking observations of distant galaxies. He measured their distances using variable stars called Cepheids, whose brightness pulsates in a predictable pattern that reveals their true luminosity. By comparing this true brightness with their apparent brightness as seen from Earth, he could calculate their distance. Then he measured their velocities by examining their light spectrum. Every element emits light at specific wavelengths, creating a unique spectral signature. When an object moves away from you, these wavelengths stretch. They shift toward the red end of the spectrum, a phenomenon called redshift. What Hubble found was stunning in its simplicity and profound in its implications. Every galaxy he observed showed redshift. Every single one was moving away from us. And the farther away the galaxy, the greater its redshift, the faster it was receding. He quantified this relationship in what became known as Hubble's law. Velocity equals distance multiplied by a constant, now called the Hubble constant. A galaxy twice as far away recedes twice as fast. A galaxy 10 times more distant recedes 10 times faster. This pattern made sense only if the entire universe was expanding uniformly. If galaxies were just randomly scattered and moving in various directions, Some would show redshift and others would show blueshift as they approached us. But universal expansion explained everything. It meant that long ago, everything was closer together. Extrapolating backward, Hubble's observations implied the universe had a beginning, a moment when all space, all matter, all energy was compressed into an infinitesimally small point. This was the origin of Big Bang theory, though that dismissive name came from skeptic Fred Hoyle, who preferred the steady-state model of an eternal, unchanging cosmos. The mathematics of expansion come from Einstein's field equations of general relativity, specifically their application to a uniform, homogeneous universe. These Friedmann equations, developed by Alexander Friedmann in 1922, describe how the scale factor of the universe, essentially its size, changes over time. They reveal something remarkable. A static universe is unstable. It cannot exist. Any tiny perturbation, any slight imbalance will cause the universe either to collapse inward under its own gravity or to expand outward. Stasis is impossible. This is why Einstein's cosmological constant, his attempt to force the equations to allow a static universe, was actually working against the natural behavior of space-time. When Hubble's observations confirmed expansion, Einstein reportedly called the cosmological constant his greatest blunder. The universe wanted to be dynamic. The equations naturally predicted change. Trying to prevent that was like trying to balance a pencil perfectly on its point. Theoretically possible, but practically impossible, and any tiny deviation leads immediately to dramatic change. To put this in perspective, consider the actual scale of cosmic expansion. The current value of the Hubble constant is approximately 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. This means that for every 3.226 million light-years of distance between 2 points in space, those points are separating at an additional 70 kilometers per second. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away, close enough that gravity still dominates and we're actually heading toward a collision in about 4 billion years. But a galaxy 10 million light-years away is receding at roughly 200 kilometers per second. A galaxy 100 million light-years distant is receding at 2,000 kilometers per second. At a billion light-years, the recession velocity reaches 20,000 kilometers per second, 6% the speed of light. Here's what makes this truly mind-bending. There are galaxies so distant that the space between us and them is expanding faster than light can travel. This doesn't violate relativity because nothing is actually moving through space faster than light. Space itself is expanding, which has no speed limit. The light from these galaxies is traveling toward us at light speed, but the space between us is stretching faster than the light can cross it. That light is running on a cosmic treadmill set faster than its maximum sprint, losing ground with every passing moment. We will never see those galaxies as they exist now. The light from their current state will never reach us. They are beyond our cosmic horizon, permanently and irrevocably. And this brings us to the crucial question that will occupy us for the rest of this journey. Why doesn't gravity stop this expansion? Gravity is attractive. It pulls things together. Every atom in the universe exerts gravitational attraction on every other atom. With all this matter pulling inward, why doesn't the expansion slow down and eventually reverse? For decades after Hubble's discovery, physicists assumed it would. They calculated that the universe must either be expanding fast enough to overcome its own gravity and expand forever, or slowly enough that gravity would eventually win, halting expansion and triggering a collapse, a big crunch that would end in a singularity similar to the one that began everything. The universe, they thought, was like a ball thrown upward. Either it had enough velocity to escape Earth's gravity and fly off into space forever, or it would slow down, stop, and fall back down. What no one anticipated was that the ball would start accelerating upward after being thrown, as if gravity had suddenly reversed into repulsion. But that's exactly what observations revealed in 1998, and it changed everything we thought we understood about cosmic destiny. The expansion of the universe isn't coasting on momentum from the Big Bang. It's being actively accelerated by something we don't understand, something that dominates the energy content of the entire cosmos, something that ensures nothing, absolutely nothing, can stop the expansion, ever. Chapter 2: Hidden Acceleration. For 70 years after Hubble's discovery, cosmologists operated under a reasonable assumption: the expansion of the universe must be slowing down. Gravity pulls matter together. The universe contains vast amounts of matter, stars, galaxies, gas, dust, dark matter, all exerting attractive gravitational force on everything else. This collective gravity should act as a cosmic brake, gradually slowing the expansion that began with the Big Bang. The only question was whether the universe had enough matter to eventually halt expansion completely and trigger a collapse, or whether it would expand forever, but at an ever-decreasing rate, asymptotically approaching zero expansion speed. This was the debate that dominated cosmology through the late 20th century. Astronomers measured the density of matter in the universe and compared it to the critical density, the precise amount needed to make the universe spatially flat, balanced perfectly between eternal expansion and eventual collapse. Below critical density, the universe was open and would expand forever. Above critical density, it was closed and doomed to end in a big crunch. At exactly critical density, it was flat, expanding forever, but just barely, with the expansion rate approaching zero infinitely slowly. Observations suggested the universe was close to flat but seemed to lack sufficient visible matter. This led to the discovery and acceptance of dark matter in the 1970s and 1980s. Invisible matter that doesn't emit light but exerts gravitational influence, explaining why galaxies rotate faster than visible matter alone could account for. Dark matter appeared to comprise about 85% of all matter in the universe, with ordinary matter making up just 15%. Even adding dark matter, though, the total matter densities seemed to fall short of the critical value. The universe appeared to be open, destined for eternal expansion, but slowing down. Then came 1998 and everything changed. Two independent research teams, the Supernova Cosmology Project led by Saul Perlmutter and the High Z Supernova Search Team led by Brian Schmidt and Adam Rees, were studying distant type Ia supernovae to measure the expansion rate of the universe at different cosmic epochs. Type Ia supernovae are remarkably useful for cosmology because they're standard candles. Their peak brightness is consistent and predictable, allowing astronomers to determine their distance by comparing their apparent brightness with their known true brightness. The teams observed supernovae billions of light-years away, seeing the universe as it existed billions of years ago. By measuring the redshift of these explosions and their distances, they could map out how the expansion rate had changed over cosmic history. Everyone expected to quantify the deceleration, to measure exactly how much gravity had slowed the expansion over the past several billion years. Instead, they found the opposite. The distant supernovae were dimmer than expected, which meant they were farther away than expected for their redshift. The expansion rate in the past was slower than the expansion rate today. The universe wasn't decelerating, it was accelerating. This discovery was so unexpected, so contradictory to theoretical predictions, that both teams initially assumed they'd made an error. They checked their instruments, their methodology, their calculations. They looked for systematic biases, maybe dust between us and the supernovae was making them appear dimmer than they really were. Maybe the early universe produced different types of supernovae than we see today. Maybe gravitational lensing by intervening matter was affecting the measurements. Every alternative explanation failed. The conclusion became inescapable. Approximately 5 to 6 billion years ago, the expansion of the universe stopped decelerating and began accelerating. Some unknown force or energy had overcome gravity and taken control of cosmic evolution. The nature of this force remained completely mysterious, but its effects were undeniable. Astronomers called it dark energy. Dark because it doesn't interact with light or any other electromagnetic radiation. Energy because it manifests as a form of energy density filling all of space. The implications were staggering. Dark energy doesn't just exist, it dominates. Detailed measurements over the following decades, including data from the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, revealed the cosmic energy budget with remarkable precision. Dark energy comprises approximately 68% of all energy in the universe. Dark matter makes up about 27%. Ordinary matter, everything made of atoms, everything we can see, every star and planet and person, amounts to just 5% of the total. We live in a universe where 95% of the content is completely invisible and poorly understood, and the dominant component is actively pushing everything apart. Dark energy behaves unlike anything else in physics. Normal matter and energy become less dense as the universe expands. If you have a certain amount of gas in a box and you make the box bigger, the density decreases. But dark energy appears to maintain constant density even as space expands. Create more space and you create more dark energy. It's as if dark energy is a property of space itself, an intrinsic energy density associated with the vacuum. As the universe expands and the volume of space increases, the total amount of dark energy increases proportionally. This property, constant density despite expansion, is exactly what Einstein's cosmological constant predicted. Remember, Einstein introduced this term to counteract gravity and prevent his equations from predicting cosmic expansion or contraction. He set the value to precisely balance gravity and maintain a static universe. But a cosmological constant with a positive value doesn't create stasis, it creates accelerated expansion. It acts as a repulsive force, or more accurately, as negative pressure that pushes space apart. In thermodynamics, pressure is typically positive. It pushes outward on the walls of a container. But negative pressure effectively pulls outward, stretching space itself. This is counterintuitive because we have no everyday experience with negative pressure. Imagine trying to compress a spring. The spring exerts positive pressure, resisting compression. Now imagine a spring that, when compressed, pulls itself even further compressed. That's negative pressure. In the context of cosmic expansion, negative pressure causes space to expand faster as the universe grows. The mathematics suggest that dark energy density remains constant at approximately 6x1010 joules per cubic meter. This seems like an absurdly tiny amount, roughly equivalent to the mass energy of 6 hydrogen atoms per cubic meter of space. But space is enormous and this energy adds up. More importantly, while matter density decreases as the universe expands, dark energy density stays the same. This means dark energy's influence grows over time relative to matter's influence. Early in cosmic history, when the universe was much smaller and denser, matter dominated. Gravity overwhelmed any effect from dark energy. The universe expanded due to its initial conditions from the Big Bang, but this expansion decelerated as gravity pulled everything back together. As the universe grew and matter became more dilute, gravity's influence weakened. Eventually, around 5 to 6 billion years ago, dark energy's influence surpassed gravity's. From that point forward, acceleration began and has continued ever since. To put this in perspective, consider two galaxies currently separated by 100 million light-years. Right now, the space between them is expanding such that they're separating at about 2,000 kilometers per second. But they're not just maintaining that separation velocity, they're accelerating. Next year, they'll be separating slightly faster. In a million years, noticeably faster. In a billion years, dramatically faster. The farther apart things get, the more space exists between them, the more dark energy contributes to their separation, and the faster they accelerate away from each other. This creates a runaway process. Expansion creates more space, which contains more dark energy, which accelerates expansion, which creates more space, and so on in an endless feedback loop. There's no break on this process, there's no mechanism to slow it down, and this brings us to the fundamental question: couldn't some force, some phenomenon, some cosmic mechanism stop or reverse this acceleration? What if gravity somehow got stronger? What if dark energy changed its properties? What if the universe reached some limit? The answer to every hypothetical escape is the same: no. And understanding why reveals profound truths about the nature of physical law, cosmic evolution, and the ultimate fate of everything that exists. Chapter 3: Impossible Reversal. Let's consider every possible mechanism that might halt or reverse cosmic expansion and understand precisely why each one fails. This isn't speculation or philosophical musing, it's an examination of fundamental physical constraints that make stopping expansion as impossible as traveling faster than light or violating conservation of energy. First, the most obvious candidate: gravity. Gravity is attractive. It pulls matter together. In principle, if the universe contained enough matter, collective gravitational attraction could overcome expansion, eventually halt it, and initiate a collapse back toward a big crunch. This scenario, called a closed universe, was seriously considered for decades. The mathematics of general relativity allow for it if matter density exceeds the critical density, but observations have definitively ruled this out. The universe's matter density is below the critical threshold. Dark matter adds significantly to the total, bringing us close to critical density, but not over it. Even combining all ordinary matter and all dark matter, we reach only about 32% of the universe's total energy content. That's not enough to overcome expansion momentum, and it's nowhere near enough to overcome accelerated expansion driven by dark energy. Moreover, gravity becomes weaker as distances increase. The gravitational force between two objects decreases with the square of the distance between them. Double the distance, and gravity drops to 1/4 strength. As cosmic expansion increases distances between galaxies, the gravitational forces pulling them together become progressively weaker. Meanwhile, dark energy density remains constant. The balance tips further in favor of expansion with each passing moment. Could gravity somehow become stronger? Could some modification of general relativity change how gravity behaves at cosmic scales? Physicists have explored modified gravity theories extensively, models where gravitational attraction doesn't follow precisely the inverse square law at enormous distances, where additional terms in Einstein's equations alter cosmic dynamics. Some of these theories were developed specifically to explain cosmic acceleration without invoking dark energy. Every modified gravity theory that attempts to explain acceleration makes predictions about other observable phenomena: the cosmic microwave background radiation, the large-scale structure of galaxy distribution, the growth rate of cosmic structures over time. Observations have systematically ruled out virtually all alternative theories. General relativity, supplemented by dark energy, matches observations with remarkable precision. Modifications either fail to explain acceleration or make other predictions that contradict what we observe. Gravity, it appears, behaves exactly as Einstein predicted, and it's simply too weak at cosmic scales to counteract dark energy's influence. What about the properties of dark energy itself? Could dark energy be unstable? Could it decay or transform into something else, removing the accelerating force? This is theoretically possible, and physicists have proposed various dark energy models beyond a simple cosmological constant. These models, collectively called quintessence, involve a dynamic field that changes over time, potentially varying in strength or even reversing from acceleration to deceleration. The evidence argues against this. Observations of cosmic expansion at different epochs, measurements of the cosmic microwave background, and studies of structure formation all indicate that dark energy has remained remarkably constant over billions of years. Its density hasn't changed appreciably, its effects haven't weakened, and there's no indication of any instability or evolution. If dark energy truly is equivalent to Einstein's cosmological constant, then it's a fundamental property of space-time itself, as unchanging as the speed of light or Planck's constant. Even if dark energy somehow began decreasing, it wouldn't reverse expansion. It would merely slow the acceleration. The universe would still expand forever, just at a less rapidly increasing rate. To actually stop and reverse expansion would require dark energy to become negative, to transform from negative pressure pushing space apart to positive pressure pulling space together. There's no known physical mechanism that would cause such a transition, and no observational evidence suggesting it's even remotely possible. Consider phase transitions. In particle physics and cosmology, phase transitions occur when a field's energy configuration changes dramatically, like water freezing into ice. The early universe underwent several phase transitions as it cooled after the Big Bang, moments when fundamental forces separated and particles acquired mass through the Higgs mechanism. Could dark energy undergo a phase transition that eliminates or reverses its effects? Theoretically, perhaps. But such a transition would need to occur simultaneously throughout the entire observable universe, affecting all of space at once. Phase transitions typically propagate at or below the speed of light, spreading from nucleation points. A phase transition traveling at light speed from some origin point wouldn't stop expansion. It would create an expanding bubble of altered space-time, but the universe outside that bubble would continue accelerating away faster than the bubble boundary could expand to catch it. You can't reverse cosmic expansion faster than cosmic expansion itself increases distances. What about quantum effects? Could quantum mechanics somehow constrain or reverse expansion at extreme scales? Quantum field theory describes how fields fluctuate at the smallest scales, creating temporary particle-antiparticle pairs that pop into existence and annihilate almost instantly. These vacuum fluctuations contribute to what physicists call zero-point energy, the minimum energy that quantum fields possess, even in their ground state. Some physicists have proposed that dark energy might be related to this zero-point energy of quantum fields. The problem is that naive calculations predict vacuum energy density that's 120 times larger than observed dark energy. This is called the cosmological constant problem, and it's one of the most severe fine-tuning problems in physics. Why is dark energy so small compared to theoretical predictions? No one knows. But regardless of dark energy's origin, quantum effects don't provide any mechanism to stop expansion. Quantum mechanics operates at subatomic scales, while cosmic expansion occurs at scales of millions of light-years. The quantum realm influences the cosmic realm only through its contribution to overall energy density, which we already account for. There's no quantum phenomenon that reaches across billions of light-years to coordinate a slowdown or reversal of expansion. Could some future advanced civilization develop technology to manipulate space-time itself, creating regions of altered expansion? This sounds like science fiction, but let's consider it seriously. To affect cosmic expansion locally, you'd need to manipulate space-time curvature on enormous scales using gravitational effects. This requires energy, vast, almost incomprehensible amounts of energy. General relativity tells us that positive energy curves space-time in ways that create attractive gravity. To counteract dark energy's negative pressure, you'd need to create immense concentrations of matter or energy. But concentrating enough energy to noticeably affect space-time on cosmic scales would create black holes. You can't compress that much energy into a region without exceeding the Schwarzschild radius and forming an event horizon. Any civilization trying to stop cosmic expansion locally would succeed only in creating black holes that would trap their own galaxy not halt the expansion of space around them. Perhaps most fundamentally, cosmic expansion doesn't occur in any frame of reference that could be acted upon. When you push an object, you're transferring momentum through electromagnetic forces between electrons in your hand and electrons in the object. When you launch a rocket, you're expelling mass in one direction to generate momentum in the opposite direction. All of these actions occur within space-time, affecting objects moving through space. But cosmic expansion is the evolution of space-time itself. There's no external reference frame from which to grab space and slow it down. There's no substance to push against, no mechanism to apply force to the fabric of reality. Asking how to stop cosmic expansion is like asking how to prevent time from flowing forward. It's a category error that misunderstands what expansion fundamentally is. The universe is expanding because that's what universes do. The equations of general relativity, applied to a uniform distribution of matter and energy, naturally yield dynamic solutions. Static configurations are unstable, impossible to maintain. And once you add dark energy, whether it's Einstein's cosmological constant or some other field, accelerated expansion becomes the inevitable outcome. There's no escape, no reversal, no mechanism for stasis. This isn't a limitation of current technology or understanding. This is fundamental constraint built into the structure of physical law. And it leads us to confront an uncomfortable reality. The cosmos we inhabit is temporary, changing, rushing toward a future radically different from the present. Chapter 4. Dark Dominance. To truly understand why nothing can stop cosmic expansion, we need to confront what dark energy actually is, or more precisely, what we know, what we suspect, and what remains utterly mysterious about this dominant component of reality. Dark energy isn't just important because it accelerates expansion. It's important because it reveals how little we understand about the universe we inhabit, and because its properties are so precise, so specific, that they seem almost impossibly fine-tuned for cosmic evolution. Let's start with what we know definitively. Dark energy comprises approximately 68% of the universe's total energy content. Its density is roughly 6 × 1010 joules per cubic meter, equivalent to about 6 hydrogen atoms worth of mass energy in every cubic meter of space. This density has remained essentially constant throughout the observable history of the universe, at least over the past several billion years. It exerts negative pressure, about -1 times its energy density, which in general relativity creates a repulsive gravitational effect that drives accelerated expansion. These properties match perfectly with Einstein's cosmological constant, which he introduced in 1917 and abandoned in 1929. The cosmological constant is simply a term added to the Einstein field equations, represented by the Greek letter lambda, L. It represents the energy density of empty space itself, a kind of baseline energy that exists even in a perfect vacuum devoid of matter, radiation, or any other form of conventional energy. Here's where it gets strange. In quantum field theory, empty space isn't actually empty. Quantum fields permeate all of space, and their quantum fluctuations create temporary particle-antiparticle pairs that exist for infinitesimally brief moments before annihilating. These fluctuations contribute to the vacuum energy, the energy of empty space. When physicists calculate the expected vacuum energy from quantum field theory, they get an answer that's catastrophically wrong. The calculated value is approximately 10^120 times larger than the observed dark energy density. This isn't just wrong, it's wrong by a margin so vast that it represents perhaps the worst prediction in the history of science. If dark energy actually had the value quantum field theory naively predicts, the universe would have torn itself apart almost instantly after the Big Bang. No atoms could form, no stars could exist, no life could emerge. The fact that we exist at all means dark energy is far, far smaller than theoretical calculations suggest. Why? No one knows. This is the cosmological constant problem, and it's one of the deepest mysteries in fundamental physics. It suggests that either quantum field theory is missing something crucial in how it calculates vacuum energy, or there's some unknown mechanism that cancels out almost all the predicted vacuum energy, leaving just the tiny residue we observe as dark energy. Various theories attempt to explain this: supersymmetry, which predicts particles that might cancel vacuum energy contributions; string theory, which operates in higher dimensions where vacuum energy might behave differently; anthropic arguments that suggest we observe this particular value because universes with other values couldn't support observers. None of these explanations are fully satisfactory, and none have been confirmed by experiment or observation. The cosmological constant problem remains unsolved, a glaring gap in our understanding of fundamental physics. Yet despite not understanding its origin, we can measure dark energy's effects with remarkable precision and understand how those effects determine cosmic destiny. Dark energy's negative pressure is key. In thermodynamics and fluid mechanics, pressure is typically positive. It pushes outward. If you have gas in a container and you compress the container, the gas resists compression by exerting pressure on the walls. The energy required to compress the gas increases the gas's internal energy. But dark energy behaves oppositely. Expanding space doesn't dilute dark energy, it creates more of it. The universe's total dark energy increases as space expands. This creates a feedback loop that guarantees accelerating expansion. Imagine two galaxies separated by a certain distance. The space between them expands, increasing their separation. As more space comes into existence between them, more dark energy comes into existence in that space. This additional dark energy accelerates expansion further, creating even more space, which contains even more dark energy, accelerating expansion even more. The process amplifies itself exponentially. Consider the math. The Friedmann equations describe how the scale factor of the universe, essentially its size, changes over time. When matter dominates, the universe's expansion decelerates because gravity pulls matter together, and this gravitational attraction grows stronger as matter clumps into galaxies and galaxy clusters. But when dark energy dominates, the equations predict exponential expansion, growth at a rate that itself increases over time. Exponential growth is relentless. If something grows linearly, it increases by a constant amount per unit time. Add the same amount each second, each year, each millennium. But if something grows exponentially, it increases by a constant factor per unit time. Double every second, every year, every millennium. Exponential growth starts slowly but eventually overwhelms any linear process. A penny that doubles in value every day is worth $1.28 after a week, but over $10 million after a month. That's the power of exponential growth. Cosmic expansion driven by dark energy is exponential. This means that eventually, and we're already well into the eventually phase, dark energy will completely dominate over all other influences. Matter's gravitational attraction becomes negligible. Radiation becomes irrelevant. The only force that matters on cosmic scales is dark energy's negative pressure pushing space apart. Current observations suggest we live in what cosmologists call the lambda CDM model universe. Lambda representing the cosmological constant, dark energy, and CDM standing for cold, dark matter. In this model, the universe's far future is dominated entirely by dark energy. The observable universe will eventually contain only our local group of gravitationally bound galaxies, while everything else recedes beyond the cosmic horizon, becoming forever unreachable. But here's something that makes dark energy even stranger. Its density seems precisely calibrated to a value that allowed structure formation in the universe. If dark energy were significantly stronger, even just 10 times its current value, it would have begun dominating much earlier in cosmic history, when the universe was smaller and denser. Gravity would never have had time to pull matter into galaxies. The universe would be a smooth, featureless expanse of increasingly dilute gas, expanding too rapidly for gravitational collapse to occur anywhere. If dark energy were much weaker, say 1/10 its current value, matter would have dominated for much longer, possibly forever. The universe might have contained even more structure, even denser galaxy clusters. But the delicate balance we observe seems almost suspiciously convenient for cosmic evolution that produces complexity, structure, and eventually life. This has led some physicists to invoke the anthropic principle, the idea that we observe these particular properties because only universes with these properties can produce observers to make the observations. In a multiverse containing countless universes with varying dark energy values, only those with finely tuned values would develop complexity sufficient for consciousness to emerge. We necessarily find ourselves in one of those rare universes because we couldn't exist in the others. This reasoning makes many physicists uncomfortable. It feels like giving up on finding a deeper physical explanation, replacing "why is the universe this way?" with "because if it weren't, we wouldn't be here to ask." But the alternative, accepting that the fundamental constants of nature are simply arbitrary, requiring no explanation, is equally troubling. The cosmological constant problem remains one of the most profound unsolved questions in physics. What we can say with certainty is that dark energy's dominance is permanent. Unlike matter, which can be converted to radiation or fall into black holes, dark energy cannot be destroyed or transformed. It's not made of particles that can decay. It's not a field that can dissipate. If it truly is Einstein's cosmological constant, then it's literally a property of space-time geometry, as fundamental and unchangeable as the dimensionality of space. This means the accelerated expansion we observe today will continue forever and will intensify. The expansion rate won't remain constant, it will increase. 1 billion years from now, galaxies will be receding faster than they are today. 10 billion years from now, faster still. 100 billion years from now, the cosmic horizon will have shrunk dramatically, with fewer galaxies visible from our position than we can see today. Dark energy doesn't just accelerate expansion, it guarantees an eventual state of maximum isolation. Each gravitationally bound structure, our local group of galaxies, other galaxy clusters, individual galaxies that aren't part of groups, will become a separate, isolated island in an expanding cosmic ocean. The space between these islands will grow so rapidly that no signal, no light, no information can ever pass from one to another. They will be causally disconnected, essentially separate universes unto themselves, even though they technically exist in the same cosmos. This isolation is already beginning. There are galaxies we can see today whose current state we will never observe. The light they're emitting right now at this moment will never reach us because the space between us is expanding too rapidly. We see them as they were billions of years ago when the light now reaching us began its journey. But their present-day selves have already crossed our cosmic horizon. They are already gone from our universe in every meaningful sense. And this brings us to the truly disturbing realization: dark energy doesn't just drive expansion, it actively erases evidence of cosmic history. Eventually, the cosmic microwave background radiation will become so stretched and diluted that it will be undetectable. Future astronomers, billions of years from now, will have no way to discover that the universe had a hot, dense beginning. They'll see only their local galaxies in an otherwise empty cosmos, expanding into perfect darkness. The very tools we've used to understand cosmic history will be unavailable to them. This isn't speculation. It's mathematics. The equations of general relativity combined with dark energy's observed properties predict this future with confidence. And there's no escape from it, no way to preserve evidence of the larger cosmos, because the expansion that erases this evidence is accelerating beyond any possibility of reversal. Chapter 5. Cosmic Runaway. Exponential growth is one of the most powerful and counterintuitive concepts in mathematics, and it's the key to understanding why cosmic expansion becomes absolutely irreversible over time. When dark energy dominates cosmic dynamics, the universe doesn't just expand, it enters a runaway state where expansion accelerates without limit, where distances double, then double again in ever shorter time periods. This creates a future that's not just different from the present, but fundamentally alienated from it. Let's make this concrete. Right now, the Hubble constant, the rate of cosmic expansion, is approximately 70 kilometers per second per megaparsec. A galaxy 1 megaparsec away, about 3.226 million light-years, recedes at 70 kilometers per second. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. A galaxy 1,000 megaparsecs away recedes at 70,000 kilometers per second, nearly 1/4 the speed of light. But this rate itself is changing. Dark energy is causing the Hubble constant to evolve in a specific way. As the universe expands and dark energy comes to dominate more completely over matter, the expansion rate approaches an exponential form. Mathematically, this means the scale factor of the universe, its size, grows as e Shitia, where a is Euler's number, approximately 2.718, h is the Hubble parameter, and t is time. This is exponential expansion, also called de Sitter expansion, after Willem de Sitter, who studied such solutions to Einstein's equations in 1917. In exponential expansion, the universe doubles in size at regular intervals. Currently, at the observed rate, the universe's scale factor doubles approximately every 12 billion years. This means that 12 billion years from now, the distance between any 2 points not gravitationally bound to each other will be twice what it is today. Another 12 billion years later, it will be 4 times today's distance. Another 12 billion years, 8 times. Another 12 billion years, 16 times. Notice something crucial. The time between doublings remains constant, but the absolute increase in distance gets larger with each doubling. Going from 1 to 2 is adding 1 unit. Going from 2 to 4 is adding 2 units. Going from 4 to 8 is adding 4 units. Going from 1024 to 2048 is adding 1024 units. The same time interval produces ever larger absolute changes. This is why exponential growth seems slow at first, but eventually becomes overwhelming. It's adding increasing amounts with each step. For cosmic expansion, this means galaxies currently just beyond our cosmic horizon, whose light can barely reach us, will soon cross a threshold where they become permanently unreachable. The space between us and them will be expanding so rapidly that even if they emitted light at this moment, that light would never reach us. It would be like trying to swim upstream in a river that flows faster than you can swim. Every stroke moves you forward through the water, but the water itself carries you backward faster than you can compensate. This is already happening to distant galaxies. The cosmic horizon, the boundary beyond which objects recede faster than light, is approximately 14 billion light-years away in co-moving distance, a distance measure that accounts for expansion. Galaxies beyond this boundary are receding so rapidly that light emitted from them now will never reach us. We can see galaxies beyond this distance, but only because we're seeing light they emitted long ago, when they were closer and when expansion was slower. Their current state is already forever invisible to us. As exponential expansion continues, this horizon will shrink in terms of what new information can reach us. Currently, we can receive new light from objects up to about 16 billion light-years away, seeing them as they existed in the past. But every year, some fraction of the universe crosses the threshold where even past light can no longer reach us. The observable universe isn't growing, it's shrinking in terms of what we can newly observe. Consider the Andromeda Galaxy, our nearest large galactic neighbor. Currently about 2.5 million light-years away, it's actually moving toward us, not away. Why? Because at this relatively close distance, the mutual gravitational attraction between the Milky Way and Andromeda dominates over cosmic expansion. Gravity wins locally. In about 4 billion years, the two galaxies will collide and eventually merge into a single elliptical galaxy that astronomers have nicknamed Milkomeda or Milkdromeda. This merged galaxy, along with the several dozen smaller galaxies in our local group, will remain gravitationally bound even as cosmic expansion continues, but every galaxy outside our local group will recede beyond reach. The Virgo cluster, currently about 50–60 million light-years away and containing thousands of galaxies, will fade from view. The Coma cluster, the Hercules cluster, the massive galaxy clusters that currently decorate our deep space images, all will disappear beyond the cosmic horizon. Eventually, in roughly 150 billion years, any observer in our merged local group will see a universe that appears to contain only the galaxies in their immediate vicinity. The space beyond will be perfectly dark, no distant galaxies, no quasars, no cosmic microwave background radiation detectable. The CMB will have been stretched to wavelengths so long and energy so low that it becomes indistinguishable from the zero-point energy of space itself. The evidence that the universe ever contained anything beyond the local group will have been erased by expansion. This creates a profound epistemological problem for future astronomers. How will they know the universe had a beginning? How will they discover the Big Bang, understand cosmic evolution, measure the age of the cosmos? The key evidence we've used, redshift of distant galaxies, the cosmic microwave background, the abundance of light elements from primordial nucleosynthesis, will be unavailable. They'll inhabit a universe that appears static and eternal, much like the universe our ancestors imagined we lived in before Hubble's discoveries. There's a disturbing thought experiment here. Perhaps we're already in that situation. Perhaps our observable universe is just a small patch of a much larger cosmos, and expansion has already erased evidence of what lies beyond. Perhaps civilizations that existed trillions of years ago could see a cosmos far richer, more complex and more extensive than we can observe. We may already be cosmologically impoverished compared to observers in the deep past, and we have no way to know it. But let's make this even more extreme. Exponential expansion doesn't stop at isolating galaxy clusters. Eventually, it accelerates to the point where it begins affecting smaller scales. Current expansion is negligible within galaxies, solar systems, or smaller structures because gravity, electromagnetic forces, and other interactions hold these systems together against expansion. The forces binding atoms together, planets to stars, stars to galaxies, these are vastly stronger than the extremely gentle stretching of space caused by dark energy. However, exponential growth means expansion accelerates forever. There's a theoretical point far in the future, perhaps 1022 years or more from now, when expansion becomes so rapid that it begins to overcome even these binding forces. This is called the Big Rip scenario, though it only occurs if dark energy density increases over time rather than remaining constant. If dark energy truly is Einstein's cosmological constant with perfectly fixed density, the Big Rip won't happen. But if dark energy is instead a dynamical field that can strengthen, then eventually the expansion rate becomes so extreme that it tears apart galaxies, then solar systems, then planets, then atoms, then atomic nuclei, and finally, even the fabric of space-time itself. Current observations suggest dark energy is consistent with a cosmological constant density, unchanging properties. This means we're headed for exponential expansion, not a big rip. But the distinction matters less than you might think. Even without a big rip, exponential expansion eventually creates a universe where every gravitationally bound structure is alone in an infinite darkness, where the night sky shows no stars beyond your own galaxy, where the cosmic microwave background has faded to nothing, where no new information arrives from beyond the cosmic horizon. It's a form of heat death, maximum entropy, maximum isolation, ultimate stagnation. This is the cosmic runaway. It's not a sudden catastrophe, but a gradual acceleration that becomes more pronounced with each passing billion years. The universe isn't falling off a cliff, it's on an exponential curve that starts almost flat, but eventually turns vertical, reaching toward infinity. And because this acceleration is driven by the dominant energy component of the entire cosmos, nothing can slow it down or stop it. Not gravity, not matter, not radiation, not any force or field that we know of or can imagine. The universe is accelerating away from structure, complexity, and connectedness towards simplicity, isolation, and darkness. And this brings us to confront what this actually means for the far future, not just for galaxies and cosmic horizons, but for stars, planets, and any form of life or complexity that might persist in this expanding cosmos. Chapter 6: Future Isolation. Let's follow the timeline of cosmic expansion forward and understand precisely what the universe will become. This isn't speculation or philosophical musing, it's applying well-understood physics to the known properties of dark energy and matter. The future isn't uncertain, it's calculable, and what the calculations reveal is a cosmos that becomes progressively more alien, more empty, and more isolated until it reaches a state of absolute thermodynamic equilibrium from which nothing can ever deviate again. Start with the relatively near future, the next few billion years. Currently, the universe is about 13.8 billion years old. In roughly 4 billion years, the Andromeda Galaxy will collide with the Milky Way. This sounds violent, but galactic collisions are surprisingly gentle. The vast distances between stars mean that actual stellar collisions are extraordinarily rare. Instead, the galaxies will pass through each other like two clouds interpenetrating, with gravitational interactions flinging some stars into intergalactic space and redistributing others. Over perhaps 1 billion years of repeated encounters, the two spiral galaxies will merge into a single elliptical galaxy. By this time, about 5 billion years from now, our Sun will be entering its red giant phase, expanding to potentially engulf Earth's orbit. The habitability of Earth will have ended long before, as the Sun's gradually increasing luminosity will have boiled away our oceans in perhaps 1 billion years, but other stars will still be forming, and the merged Milky Way Andromeda system will remain a vibrant, active galaxy with billions of years of star formation ahead of it. At this 5 billion year mark, cosmic expansion will have increased all extragalactic distances by approximately 50%. Galaxies currently 100 million light-years away will be 150 million light-years distant. The Virgo cluster will appear noticeably more distant and dimmer. But the night sky will still contain millions of visible galaxies, and the cosmic microwave background will still be detectable, though slightly cooler and more redshifted than today. Move forward to 20 billion years from now, less than 35 billion years after the Big Bang. The universe will have doubled in size since today. Galaxies, currently at the edge of observability, will have crossed the cosmic horizon permanently. But the more significant change is what's happening to stars. Star formation requires cold gas that can collapse under gravity. As the universe ages, more and more of the available gas gets locked into stars, stellar remnants, or black holes. Less fuel remains for new star formation. By 1 trillion years from now, yes, trillion with a T, star formation will have essentially ceased throughout the universe. All the available hydrogen and helium will have been processed through stellar fusion or ejected from galaxies in galactic winds. The stars that remain will be mostly small red dwarfs, the longest-lived stellar type, which can burn for trillions of years. But even these will gradually exhaust their fuel and fade. Meanwhile, cosmic expansion continues accelerating. By this time, 1 trillion years in the future, every galaxy not gravitationally bound to our local group will be not just invisible, but completely beyond any causal contact. The observable universe from the perspective of our local group, now fully merged into a single massive galaxy, will contain only that local galaxy. The sky beyond will be perfectly black. No distant galaxies, no quasars, no cosmic microwave background detectable by any instrument. An observer at this time would have no direct evidence that the universe is larger than their single galaxy. Think about what this means epistemologically. These future astronomers would see a static-seeming universe, one galaxy in an infinite void. They wouldn't observe expansion directly because everything observable is gravitationally bound. They wouldn't see a cosmic microwave background. They wouldn't be able to measure the universe's age using distant supernovae or other standard candles. Their understanding of cosmology would be fundamentally limited by the fact that expansion has erased the evidence of cosmic history. This raises a profound question. Are we already in this situation? Have we missed crucial epochs of cosmic evolution that occurred so long ago that expansion has erased all evidence? There's no way to know, and that uncertainty is itself disturbing. The universe may be far older, far larger, and far stranger than we can determine from available observations. Cosmic expansion doesn't just affect the future, it obscures the past. Continue forward to 100 trillion years from now. The last red dwarfs are winking out, having exhausted their hydrogen fuel. The universe now consists primarily of stellar remnants, white dwarfs, the cooling cores of dead sun-like stars, neutron stars, the ultra-dense remains of massive stars, and black holes formed from the most massive stars or from the merger of smaller remnants. The only light comes from extremely rare events, occasional white dwarf collisions, the faint radiation from matter falling into black holes, and the incredibly dim glow of white dwarfs themselves as they gradually cool toward absolute zero. This is entering the black hole era, a phase where black holes are among the most prominent objects in the cosmos. Not because they're common, they're actually quite rare compared to stellar remnants, but because they're among the few objects still capable of energetic activity. Matter that wanders too close to a black hole gets heated to millions of degrees as it spirals inward, briefly flaring before disappearing beyond the event horizon. But even black holes are not eternal. Stephen Hawking discovered in 1974 that black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation causes black holes to gradually evaporate, losing mass over immense timescales. A black hole with the mass of our Sun would take approximately 1,067 years to evaporate completely. A supermassive black hole with 1 billion solar masses would last roughly 1,098 years. These numbers are so large they lose intuitive meaning. The current age of the universe, 13.8 billion years, is about 1010 years. We're talking about timescales 100 billion times longer than the universe has currently existed. But given infinite time, even these black holes will eventually evaporate, leaving behind only a sparse collection of photons, neutrinos, and fundamental particles spreading through an exponentially expanding space. By 100 years or so, a Google years, even the largest black holes will have evaporated. The universe will enter the dark era, dominated by an increasingly dilute gas of photons and other particles, all with energies approaching zero as they're redshifted by expansion. The temperature of space will be unimaginably close to absolute zero, not because the universe has cooled by radiating heat away, but because expansion has stretched all thermal radiation to effectively infinite wavelengths. At this point, the universe approaches maximum entropy, a state of perfect thermodynamic equilibrium where no energy gradients exist, no structure persists, and no processes occur. This is heat death, not in the sense of high temperature, but in the sense of thermodynamic death, the cessation of all activity that depends on energy flow from hot to cold regions. When everything is uniformly cold and dispersed, nothing can happen. No stars can shine because there are no stars. No life can exist because life requires energy flow, and energy flow requires gradients that no longer exist. And throughout this entire cosmic history, from today to the heat death, dark energy continues accelerating expansion. The space between any 2 points that aren't gravitationally bound continues growing exponentially. The horizon distance shrinks in terms of what can causally influence any given point. The universe becomes not just empty but disconnected, with isolated pockets of former matter separated by exponentially growing voids of expanding space-time. There is something deeply melancholic about this cosmic trajectory. The universe begins in a hot, dense state filled with intense radiation and rapid evolution. Structure forms, first subatomic particles, then atoms, then stars and galaxies. Complexity emerges, life appears, at least on Earth and possibly on countless other worlds. Consciousness arises and begins contemplating its own cosmic origins and destiny. This period of complexity and activity is cosmically brief, perhaps just a few trillion years out of an infinite future. Then comes an endless future of exponential expansion toward cold, dark, maximum entropy. The period of stars, galaxies, and complexity is an infinitesimally brief moment in cosmic history, a brief flowering between the initial Big Bang and the eternal expansion toward heat death. We exist in this narrow window, this cosmological instant, when the universe is interesting, when it contains structure, when observation and understanding are possible. Future astronomers in the trillion-year future would look back on our era with envy. They would recognize that we lived in the golden age of cosmology, when the cosmic microwave background was still visible, when distant galaxies could still be observed, when the evidence of cosmic origins hadn't been erased by expansion. We are privileged observers inhabiting a universe young enough to remember its origins and still connected enough to observe its vast structure. But this privilege comes with a sobering awareness. We're watching a process we cannot stop, observing a cosmic destiny we cannot alter, documenting a transformation toward isolation and darkness that began billions of years ago and will continue for googles of years to come. Nothing can stop it, nothing can reverse it. The universe is expanding, accelerating, and approaching heat death, and there's absolutely nothing anyone can do about it. Chapter 7. Ultimate Cold. The heat death of the universe isn't about heat in the colloquial sense. It's about the absence of usable energy, the end point of thermodynamic evolution, where entropy reaches its maximum possible value and no further change can occur. To understand why this is the inevitable fate of an expanding cosmos dominated by dark energy, we need to explore what entropy means, why it always increases, and what it means for everything to reach thermodynamic equilibrium. Entropy is often described as disorder or randomness, but more precisely, it's a measure of the number of possible microscopic configurations that correspond to the same macroscopic state. Imagine a box divided in half with all gas molecules on one side. That's a low entropy state because there's only one general configuration, molecules on this side, empty space on that side. Now open the divider and let the gas spread throughout the box. That's higher entropy because there are vastly more ways to arrange the molecules such that they're distributed throughout the entire volume rather than confined to one half. The second law of thermodynamics states that entropy always increases in isolated systems. Why? Because systems naturally evolve from less probable states to more probable states, and high entropy states are vastly more probable than low entropy states, simply because there are so many more microscopic configurations that correspond to them. It's not impossible for entropy to decrease. All the gas molecules could spontaneously move back to one half of the box. But the probability is so astronomically small that it effectively never happens on observable timescales. The universe as a whole is an isolated system. There's nothing outside it exchanging energy with it. Therefore, the universe's total entropy must increase over time. This means the universe is evolving from lower entropy configurations toward higher entropy configurations. Every irreversible process, every star that shines, every metabolic reaction, every thought in your brain increases the universe's total entropy. The arrow of time itself may be nothing more than the direction of increasing entropy, the direction in which probable futures outnumber improbable pasts. Early universe states were extraordinarily low entropy. At the moment after the Big Bang, the universe was incredibly hot and dense, but it was also remarkably uniform, almost perfectly smooth except for tiny quantum fluctuations. This uniformity represents low entropy because the matter and energy were arranged in a very specific, ordered configuration. As the universe expanded and cooled, those tiny fluctuations grew under gravitational attraction, eventually forming stars, galaxies, and galaxy clusters. This process might seem like it's creating order and lowering entropy, but actually it's increasing it. How can gravity clumping matter into stars increase entropy? Because stars are entropy-generating machines. When hydrogen fuses into helium in a star's core, some mass converts to energy according to E, mc2. This energy radiates outward as photons that eventually escape into space. Those photons carry entropy, lots of it. A single low-energy photon has more entropy than the mass energy it came from when it was part of an atomic nucleus. Stars take low-entropy nuclear fuel and convert it into high-entropy thermal radiation. The universe's total entropy increases dramatically every second as billions of stars shine. This is why stars can't last forever. Entropy increase is a one-way process. Once hydrogen is fused into helium, you can't spontaneously unfuse it back. That would decrease entropy, violating the second law. Eventually, all the hydrogen gets converted and the star runs out of low-entropy fuel. For the most massive stars, fusion continues through heavier elements until reaching iron, where fusion no longer releases energy. At that point, the star's core collapses and explodes as a supernova, ejecting its enriched material into space. This stellar cycle represents the universe gradually processing its low-entropy initial conditions into higher entropy final states. Stars form, shine, die, and their remnants drift through space. With each generation, more material becomes locked into stellar remnants that can't undergo further fusion. More energy is radiated away as photons that spread and redshift into ever lower energy states. The gradient from low entropy to high entropy is being steadily diminished. Now add cosmic expansion. Expansion doesn't just increase distances, it reduces energy density. A fixed amount of energy distributed through a larger volume means lower energy density. Photons traveling through expanding space get redshifted, stretched to longer wavelengths and lower energies. The cosmic microwave background radiation, for instance, started as intense gamma rays when it was released 380,000 years after the Big Bang. Today, it's been stretched to microwave wavelengths with a temperature of just 2.7 Kelvin, barely above absolute zero. As expansion continues, it will redshift further, cooling toward ever lower temperatures. Expansion combined with entropy increase means the universe is heading toward a state of maximum entropy and minimum energy density. All the matter will eventually be processed through stars and black holes. All the energy will be radiated away as photons that get redshifted to infinitesimal energies by expansion. Black holes themselves will evaporate through Hawking radiation, converting their mass into photons and other particles that are similarly diluted and cooled by expansion. The end point is a universe filled with an incredibly dilute, incredibly cold gas of photons and particles, all with energies approaching zero, spread through an exponentially expanding space. This is the heat death. Not a state of high temperature, but rather a state where temperature has lost meaning because there are no thermal gradients. Temperature is meaningful only when comparing different regions or objects. This is hot relative to that cold region. But if everything is uniformly at essentially zero energy, temperature is undefined. More critically, nothing can happen. All processes that generate work, store information, maintain structure, or create complexity require energy flow from higher energy states to lower energy states. When no such gradients exist, no processes occur. Consider what this means for life, intelligence, or any form of organized complexity. Life is fundamentally about maintaining local low-entropy states by increasing entropy elsewhere. Your body maintains its organized structure by consuming food, low-entropy chemical potential energy, and converting it to heat and waste products, higher entropy thermal energy. This is possible only because Earth receives low-entropy sunlight from the Sun and radiates high-entropy infrared radiation into space. The net entropy increase in the universe exceeds the local entropy decrease in your body. But in a heat-death universe, there are no energy sources, no stars shine, no energy flows. There's nowhere to dump entropy to create local order. Any structure that might temporarily exist, perhaps a random fluctuation that briefly assembles atoms into a complex molecule, would immediately dissipate because there's no energy gradient to sustain it. The universe becomes unchanging, not because it's reached perfection, but because it's reached maximum disorder, the state from which no further evolution is possible. Freeman Dyson explored whether intelligent life might persist indefinitely by slowing metabolism to match decreasing available energy. If you think slower and slower as the universe cools, might you stretch your consciousness across infinite time, experiencing infinite thoughts even as the universe approaches heat death? Dyson's conclusion was ultimately negative. Quantum mechanics sets minimum energy costs for computation and information processing. Eventually, available energy drops below these quantum minimums and no further computation is possible. Consciousness, information processing, even memory require energy expenditure, and in a heat-death universe, that energy is unavailable. Some physicists have speculated about quantum fluctuations as a possible escape from heat death. In quantum mechanics, even a perfect vacuum experiences fluctuations where particle-antiparticle pairs briefly appear and disappear. In an infinite universe experiencing infinite time, couldn't these fluctuations occasionally produce something complex, maybe even a Boltzmann brain, a spontaneous assembly of particles into a conscious mind? Theoretically, yes, but the probabilities are unimaginably small. The probability of a random fluctuation assembling even a single functional protein molecule is vastly smaller than 1 part in 10^100. The probability of fluctuating an entire conscious brain is incomprehensibly tinier. You'd need to wait timescales far longer than Google years, perhaps 10 to 100 years or more, before such a fluctuation might occur. And even then, the fluctuation would exist for an infinitesimal moment before dissipating back into maximum entropy. It wouldn't experience continued existence, wouldn't maintain memories, wouldn't constitute meaningful consciousness in any practical sense. More fundamentally, the universe's accelerating expansion means that even quantum fluctuations become increasingly difficult. Expansion dilutes energy density towards zero. Quantum fluctuations require energy to manifest particle-antiparticle pairs, and as available energy approaches zero, even these minimal fluctuations become impossible. The combination of maximum entropy and exponential expansion creates a truly final state, not just the absence of current activity, but the impossibility of any future activity. This is the ultimate cold, not simply low temperature, but the absolute end point of thermodynamic evolution. The state from which nothing can emerge, where nothing can change, where time itself becomes meaningless because there are no processes to mark its passage. The universe doesn't end in fire or ice, drama or catastrophe. It ends in a whimper, a gradual, inexorable slide into maximum entropy and minimum energy density, accelerated by dark energy's relentless expansion, approaching an infinite future of absolute nothingness. And all of this is utterly, completely inevitable. The laws of thermodynamics guarantee entropy increase. The properties of dark energy guarantee accelerating expansion. Together, they guarantee heat death. Nothing can prevent it, because preventing it would require decreasing entropy, which violates the second law, or reversing expansion, which we've already seen is impossible. The universe is heading toward ultimate cold, and there's no escape. Chapter 8. Quantum Fate. We've explored the thermodynamic destiny of the universe, but there's another layer to cosmic fate, one that operates at the smallest scales and involves the most fundamental aspects of reality. Quantum mechanics isn't just the physics of atoms and subatomic particles, it's the physics of information, uncertainty, and the very structure of existence. And it reveals why the universe's expansion toward heat death isn't just thermodynamically inevitable, it's encoded in the quantum nature of reality itself. Start with quantum field theory, the framework that describes how particles and forces work at fundamental levels. In quantum field theory, even empty space, a perfect vacuum, isn't truly empty. It's filled with quantum fields that permeate all of existence. These fields can never be entirely still. Heisenberg's uncertainty principle guarantees that they must fluctuate, creating temporary disturbances where particle-antiparticle pairs pop into existence for infinitesimally brief moments before annihilating back into the vacuum. These vacuum fluctuations are real and measurable. They affect atomic energy levels, the Lamb shift, create forces between uncharged parallel plates, the Casimir effect, and contribute to the anomalous magnetic moment of electrons. They're not just theoretical abstractions, they're demonstrable aspects of reality that influence observable phenomena. And they represent a form of energy called vacuum energy or zero-point energy that exists even in completely empty space. This vacuum energy may be related to dark energy, the mysterious force accelerating cosmic expansion. If dark energy truly is Einstein's cosmological constant, then it could be interpreted as the energy density of the vacuum itself, the baseline energy that space possesses simply by existing. The problem, as we discussed earlier, is that naive calculations of vacuum energy yield values about 120 times larger than observed dark energy. This catastrophic mismatch is the cosmological constant problem, and it suggests we're missing something fundamental about how quantum mechanics and gravity interact. But regardless of its origin, dark energy's quantum properties have profound implications for cosmic fate. If dark energy is associated with the quantum vacuum, then it's not some temporary field that might decay or dissipate. It's a fundamental property of space-time itself, as permanent and unchangeable as the quantum nature of matter. You can't turn off quantum mechanics, you can't eliminate uncertainty principle, and if dark energy is quantum vacuum energy, you can't eliminate it either. It's woven into the fabric of existence. This permanence extends to the accelerated expansion dark energy causes. Quantum mechanics is deterministic in a specific sense. The Schrödinger equation describes how quantum states evolve over time with absolute precision. Given a quantum state at one moment, you can calculate its state at any future moment. The evolution is entirely determined by the Hamiltonian operator, which encodes all the energy and interactions in the system. Applied to cosmology, this means the universe's quantum state is evolving deterministically according to the quantum analog of Einstein's field equations. The accelerated expansion we observe isn't random or contingent. It's the inevitable evolution of the cosmos's quantum state given the presence of dark energy. Stopping or reversing this expansion would require changing the universe's quantum state in a way that violates the deterministic evolution prescribed by quantum mechanics. It's not just difficult, it's fundamentally impossible within the framework of known physics. Consider information from a quantum perspective. In quantum mechanics, information cannot be destroyed. This is the principle of unitarity. When particles interact or systems evolve, The information about their initial state is preserved in the correlations of their final state, even if that information becomes practically inaccessible. Black holes seem to violate this when Stephen Hawking showed they emit thermal radiation without information content, suggesting information that falls into black holes is destroyed. This paradox haunted theoretical physics for decades. The resolution, developed by Hawking and others, is that information isn't actually destroyed, it's encoded in subtle correlations in the Hawking radiation. The radiation isn't perfectly thermal, but contains extremely subtle patterns that, in principle, preserve all the information about what fell into the black hole. This preservation of information is sacrosanct in quantum mechanics. It's as fundamental as conservation of energy or charge. But cosmic expansion creates its own information problem. When objects recede beyond the cosmic horizon, when the space between them expands so rapidly that light can never traverse it, they become causally disconnected. Information about events occurring on one side of the horizon can never reach the other side. In a universe dominated by dark energy and exponential expansion, this horizon becomes a permanent feature. Vast amounts of information become permanently inaccessible, trapped beyond boundaries that can never be crossed. Does this violate information conservation? Technically, no, because the information still exists. It's just inaccessible from certain reference frames. An observer in one causal patch of the universe can't access information in another patch, but both patches still exist, and the information in each remains preserved within its own domain. The universe as a whole preserves information, but that information becomes fragmented across causally disconnected regions that can never communicate or interact. This fragmentation is permanent and irreversible. Once two regions are separated beyond the cosmic horizon, they can never rejoin. The expansion driving them apart is accelerating exponentially, meaning the separation grows faster over time, not slower. There's no mechanism for reversing this separation because doing so would require information to travel faster than the expansion of space, which would require faster-than-light travel through space-time, a violation of relativity. Quantum entanglement might seem like a loophole. Entangled particles exhibit correlated properties regardless of the distance between them. Measure one, and you instantly know something about the other, even if it's across the galaxy. Einstein called this spooky action at a distance, and it seems to involve instantaneous influence across arbitrary distances. Could entanglement allow communication across cosmic horizons? No. Quantum entanglement cannot transmit information faster than light. The correlations between entangled particles are perfect, but they appear random to any observer until measurements from both sides are compared. To extract information from entanglement, you need classical communication to compare results, and classical communication is limited by the speed of light. Entanglement preserves correlations but doesn't enable superluminal signaling. Once two regions are separated by horizons expanding faster than light, even entangled particles can't bridge the gap for information transfer. This means the quantum state of the universe is becoming increasingly disconnected. Regions that were once in causal contact, that could exchange information and influence each other's quantum states, are becoming isolated islands with no possibility of future interaction. The universe's global quantum state is fragmenting into separate, non-interacting quantum states that might as well be different universes. This isn't speculation, it's the direct consequence of accelerated expansion in a quantum mechanical universe. Now consider measurement and observation from a quantum perspective. In quantum mechanics, measurement collapses superposition states. A particle in multiple potential states simultaneously chooses one state when observed. The Copenhagen interpretation says the act of measurement causes this collapse. But what constitutes measurement in a cosmological context? When galaxies recede beyond the cosmic horizon and become permanently unobservable, does their quantum state remain in superposition from our perspective? Are they simultaneously in all possible states because we can no longer measure them? This raises profound questions about the nature of reality in an exponentially expanding universe. If observation defines reality in quantum mechanics and vast regions of the universe become permanently unobservable due to expansion, in what sense do those regions remain real to us? They exist in our causal past. Light from them has reached us, but their current state and all future states will never be observable. They've crossed a boundary into permanent quantum inaccessibility. The many worlds interpretation offers a different perspective. In this view, quantum superpositions never collapse. All possible outcomes occur in branching parallel realities. Applied cosmologically, this suggests that every quantum event creates branches of cosmic history, and the universe we observe is just one branch of an incomprehensibly vast multiverse of quantum possibilities. Cosmic expansion doesn't just separate regions in space, it separates branches of quantum reality, creating an ever-proliferating tree of distinct cosmic histories. Whether you favor Copenhagen collapse, many worlds branching, or another interpretation, the result is similar. Accelerated expansion creates permanent separation at the quantum level. Information becomes fragmented, causal connections sever, and the universe's quantum state evolves toward maximum entropy across exponentially expanding space. The quantum fate of the cosmos mirrors its thermodynamic fate: progressive separation, isolation, and approach toward a final state of maximum disorder and minimum information accessibility. Even more fundamentally, quantum mechanics itself may impose limits on what's possible in our universe. The Bekenstein bound relates the maximum entropy, information content, of any region to its surface area and energy. This suggests that information storage is fundamentally limited. You can't cram infinite information into finite space. Applied to cosmology, this means the observable universe contains only finite information, even though it may be infinitely large beyond our horizon. As expansion continues and the cosmic horizon shrinks in terms of what new information can reach us, the total accessible information decreases. We're not just losing the ability to observe distant galaxies, we're losing access to the information those galaxies contain. Future observers will inhabit a universe with less accessible information than we have, simply because expansion has hidden more of the cosmos beyond their horizon. This represents a form of information loss that, while not violating quantum mechanics, the information still exists somewhere, represents a practical erasure of cosmic knowledge. There's something deeply troubling about this. The universe's quantum state contains the complete history of cosmic evolution. Every particle interaction, every photon emitted, every quantum fluctuation that occurred since the Big Bang. This information is encoded in the correlations between all particles and fields throughout the cosmos. But expansion is fragmenting this information, separating it across causal horizons that can never be crossed. The complete story of cosmic history exists, but no single observer, no matter how advanced, can ever access it all. This is quantum fate, not dramatic or catastrophic, but inexorable and absolute. The quantum nature of reality, combined with accelerated expansion, ensures that information becomes progressively more isolated, that causal connections permanently sever, and that the universe fragments into separate domains that evolve independently toward maximum entropy. Nothing can reverse this, because reversing it would require violating either quantum mechanics by destroying information, relativity by enabling faster-than-light communication, or thermodynamics by decreasing entropy. The quantum, thermodynamic, and relativistic aspects of cosmic fate all point in the same direction, toward a universe of isolated, maximum entropy regions separated by exponentially expanding space, with no possibility of reversal, no mechanism for reconnection, and no escape from the ultimate dissipation of all structure and complexity into the quantum vacuum. This is not merely the current trajectory, it's the only possible trajectory given the laws of physics as we understand them. Chapter 9. Human Meaning. We've explored the physical inevitability of cosmic expansion and its ultimate consequences: heat death, isolation, maximum entropy. These are the facts. Now we need to confront what these facts mean for us, for humanity, for consciousness and purpose in a universe rushing toward thermodynamic equilibrium. How do we find meaning when everything we do, everything we build, everything we discover will eventually vanish into an expanding cosmic void? This question has haunted philosophers and scientists since we first understood the universe's fate. If entropy always increases, if all structure eventually dissipates, if even the stars will die and the universe will reach a state where nothing can happen, what's the point? Why does anything matter if it's all temporary, all destined for the same entropic end? Some people find this knowledge deeply depressing. We imagine that our lives, our accomplishments, our civilizations should matter in some eternal sense, that they should leave permanent marks on the universe, that they should persist forever. But physics tells us there is no forever, at least not in the sense of eternal preservation. The universe doesn't maintain records, it increases entropy. Your thoughts, this conversation, every work of art and scientific discovery, all will eventually be erased by the relentless increase in cosmic disorder. But here's a different perspective. The temporary nature of everything doesn't diminish meaning, it creates it. Meaning isn't something that exists independently in the universe, waiting to be discovered like a physical law. Meaning is something conscious beings create through their choices, their relationships, their experiences. And temporary things can be profoundly meaningful precisely because they're temporary. Consider a sunset. You know it will end. The sun will dip below the horizon, the colors will fade, and darkness will come. Does this temporariness make the sunset meaningless, or does it make that particular sunset, that specific arrangement of light and color and atmospheric conditions that will never occur exactly the same way again, more precious, more worthy of attention? The ephemeral nature of the sunset is inseparable from its beauty. Now scale that up to cosmic proportions. The universe is in a remarkable state right now, 13.8 billion years after the Big Bang, in an epoch where stars still shine, galaxies still cluster, and complexity is possible. This epoch won't last forever. In cosmic terms, it's already brief, just a few trillion years out of an infinite future. But we exist now in this window. We're conscious beings arising from the universe's brief experiment with complexity, capable of understanding our own cosmic context. That understanding itself is extraordinary. We're arrangements of atoms that became conscious and discovered we're arrangements of atoms. We're structures temporarily existing in defiance of maximum entropy, maintaining our low entropy organized states by increasing entropy elsewhere. We're the universe looking at itself, understanding itself, marveling at its own existence. The fact that this is temporary doesn't diminish the wonder, it intensifies it. Think about what consciousness represents from a physical perspective. Your brain contains roughly 86 billion neurons, each connected to thousands of others, creating trillions of synaptic connections. These connections store information, process sensory data, generate thoughts and emotions and memories. Every thought you have is correlated with specific patterns of neural activity, electrochemical signals propagating through networks of cells. This neural activity requires constant energy expenditure. Your brain uses about 20% of your body's total energy despite being only 2% of body mass. It maintains this energy consumption every moment you're alive, processing, thinking, feeling, remembering. And all of this is powered by the low entropy chemical energy in food, which originally came from sunlight captured by plants, which came from fusion in the sun's core, which came from gravitational potential energy from the cloud that collapsed to form the sun, which came from the initial low entropy state of the Big Bang. Your consciousness is a thread connecting back to the universe's beginning, a temporary local decrease in entropy made possible by the vast entropy increases happening in stars throughout the galaxy. You exist because the universe is currently in a state where such complexity is possible, where energy gradients allow structures like brains to form and maintain themselves. This won't always be true, but it's true now. And what do you do with this consciousness, this temporary arrangement of matter that can think and feel and wonder? You experience things. You form relationships. You create and discover and explore. You find patterns in nature and call them science. You express emotions through arranged pigments or vibrations and call it art. You cooperate with other conscious beings and call it civilization. None of this is permanent. All of it matters. Consider the human species. We've existed for perhaps 300,000 years, an eye blink in cosmic time. We developed agriculture about 10,000 years ago, writing about 5,000 years ago, modern science about 400 years ago. In just the last century, we've discovered cosmic expansion, quantum mechanics, the structure of DNA, the age of the universe. We've sent spacecraft beyond the solar system, carrying messages about who we are and where we come from. We've taken photographs of galaxies billions of light years away and peered back to within 380,000 years of the Big Bang itself. All of this happened in an infinitesimal fraction of cosmic history, and it's happening in an infinitesimal fraction of the universe's volume, one small planet orbiting one ordinary star in one typical galaxy among hundreds of billions. We're tiny, recent, and temporary. And yet we've figured out the fundamental forces, mapped the cosmic microwave background, calculated the universe's fate. That's astonishing. Should we be depressed that our civilization, our entire species will eventually end? That the Earth will be consumed when the sun becomes a red giant? That even if we spread to other stars, eventually all stars will die? That even if we persist somehow for trillions of years, ultimately the universe reaches heat death and all consciousness must cease? Or should we be amazed that consciousness exists at all, that the universe's brief experiment with complexity has produced beings capable of asking these questions? That we get to participate in this epoch of stars and galaxies, that we get to understand the cosmic context we inhabit, that we get to experience wonder and love and curiosity during the narrow window when such things are possible. There's a perspective from existential philosophy that's relevant here. Jean-Paul Sartre argued that existence precedes essence. We exist first, and then we create our own meaning through our choices and actions. The universe doesn't hand us a purpose. We create purpose through how we live. Viktor Frankl, who survived Nazi concentration camps, wrote about finding meaning even in the most horrific circumstances through our attitude toward unavoidable suffering and our commitment to something beyond ourselves. Applied cosmically, this suggests that the heat death of the universe doesn't negate meaning any more than personal mortality negates the meaning of individual lives. You know you're going to die. This knowledge doesn't make your life meaningless. It makes your time precious. Similarly, the universe's eventual heat death doesn't make cosmic history meaningless. It makes this current epoch, when complexity and consciousness are possible, cosmically precious. Some physicists and philosophers have explored whether advanced civilizations might manipulate space-time, create baby universes, or exploit quantum effects to persist beyond heat death. Freeman Dyson suggested that consciousness might slow its processes to match decreasing available energy, potentially lasting forever, by thinking progressively slower thoughts. These scenarios are speculative at best and likely impossible based on quantum limits, but they represent a human impulse to seek escape from cosmic fate. But maybe escape isn't the point. Maybe the point is to exist fully and consciously during the time available, to understand what we can of the universe that produced us, to create structures of meaning and beauty that matter to us even if they don't matter to the cosmos, to connect with other conscious beings and share this brief experiment with complexity. You are an arrangement of atoms that the universe made to understand itself. When you look at stars, you're seeing photons that traveled millions or billions of years to reach your eyes, where they trigger electrochemical signals in your retina that your brain interprets as light. You are literally made of star stuff, as Carl Sagan said. The atoms in your body were forged in stellar cores and scattered through space by supernovae. You are the universe experiencing itself, contemplating its own nature, aware of its own expansion and ultimate fate. This awareness doesn't have to be depressing. It can be liberating. You don't need the universe to be eternal for your life to matter. You don't need cosmic purpose to find personal purpose. You exist now, conscious and capable of experience, in a universe briefly interesting enough to produce consciousness. That's not a curse, it's an extraordinary gift, a statistical improbability, a temporary privilege that will eventually end, but is precious precisely because it's temporary. The universe is expanding, nothing can stop it. Everything complex and structured will eventually dissipate into maximum entropy. These are the facts. But they don't prescribe how you should feel about them or what you should do with your brief moment of consciousness. That's up to you. Chapter 10. Eternal Motion. We've journeyed from the mechanism of cosmic expansion to its inevitable destination: heat death, isolation, maximum entropy. We've explored why nothing can stop this process, why every conceivable mechanism for halting or reversing expansion fails against the combined forces of dark energy, thermodynamics, and quantum mechanics. Now we need to step back and see this entire cosmic story as a unified whole, understanding what the unstoppable expansion of the universe reveals about the nature of existence itself. The universe began in an extraordinarily low entropy state, the Big Bang, a moment of infinite density and temperature that remains poorly understood. Why did the universe begin in such a low entropy configuration? Why weren't matter and energy distributed in a high entropy maximum disorder state from the start? This is called the initial entropy problem, and it's deeply connected to the arrow of time itself. We don't have definitive answers, but the fact remains: the universe started ordered and has been increasing in entropy ever since. Cosmic expansion is intimately connected to this entropy increase. As space expands, matter becomes more dispersed, energy becomes more diluted, and the universe progresses toward higher entropy configurations. Expansion isn't just a backdrop to cosmic evolution, it's a driver of that evolution, enabling structures to form because expansion cools the universe enough for atoms and molecules to exist, then eventually ensuring those structures dissipate because expansion dilutes energy sources and isolates structures from each other. The discovery of accelerated expansion transformed our understanding of cosmic fate from uncertain to certain. Before 1998, cosmologists debated whether the universe would expand forever or eventually collapse in a big crunch. That debate is over. The universe will expand forever, accelerating toward a state of maximum isolation and entropy. This isn't a theory that might be overturned by new observations. It's a measured fact that has been confirmed repeatedly by increasingly precise data from multiple independent sources. Dark energy ensures this fate is inescapable. Its constant density means it becomes increasingly dominant over time as matter becomes more dilute. Its negative pressure means it actively drives acceleration rather than simply maintaining expansion momentum. Its properties appear consistent with Einstein's cosmological constant, suggesting it's a fundamental feature of spacetime rather than a temporary field that might dissipate. Every line of evidence points to dark energy being permanent, unchanging, and utterly dominant over cosmic timescales. This permanence means the future is predictable in broad strokes, even though we can't predict specific events. We know stars will eventually exhaust their fuel. We know galaxies outside our local group will recede beyond the cosmic horizon. We know the cosmic microwave background will redshift into undetectability. We know black holes will eventually evaporate. We know the universe approaches heat death. The timeline has uncertainties. Will the last black hole evaporate in 1098 years or 10 to 100 years? But the outcome is certain. This certainty is both profound and unusual in science. Most scientific predictions come with caveats, assuming our models are correct. If no unknown forces intervene, barring revolutionary discoveries. But the heat death of an exponentially expanding universe dominated by dark energy isn't tentative. It follows necessarily from well-established physics. Avoiding it would require violating thermodynamics, quantum mechanics, or general relativity. It would require the laws of physics to be fundamentally different from what they are. Consider what this means philosophically. The universe isn't just expanding, it's evolving irreversibly toward a specific end state. This isn't cyclical, this isn't eternal recurrence, where cosmic history repeats infinitely. This is a one-way journey from low entropy to maximum entropy, from connection to isolation, from complexity to simplicity. The universe has a direction, an arrow, a fate. Yet within this grand cosmic story, there's extraordinary richness and complexity right now. The current epoch, roughly 10 billion to 1 trillion years after the Big Bang, represents the universe's most interesting phase. Stars exist, synthesizing heavy elements. Planets form, some with liquid water and complex chemistry. Life emerges and evolves. Consciousness arises and begins contemplating the cosmos. This is the universe's brief moment of self-awareness, the narrow window when complexity can examine the simple rules that govern its own existence. This window is temporary, but that temporariness doesn't diminish its significance, it defines it. If the universe was static and eternal, nothing would be special. Every moment would be like every other moment. But in a dynamic, evolving cosmos with an arrow of time, this particular moment, when stars shine, galaxies cluster, and consciousness emerges, is unique. It's unrepeatable. It will never occur again once it passes. We are extraordinarily privileged to exist during this epoch. Earlier, the universe was too hot and dense for complex structures. Later, it will be too cold and empty. Right now, conditions are perfect for complexity, for chemistry, for life, for consciousness. We didn't choose when to exist, but we happen to exist at precisely the moment when existence is most interesting, when the universe is most knowable, when discovery is most possible. This privilege comes with responsibility. We have the capability to understand our cosmic context, to discover the universe's history and fate, to appreciate the extraordinary improbability of our existence. We can either ignore this knowledge, focusing only on immediate concerns, or we can embrace it, recognizing ourselves as part of cosmic history, as temporary manifestations of the universe's brief experiment with complexity. Some find this knowledge heavy, depressing, nihilistic. If everything ends in heat death, why does anything matter? But this question assumes meaning must be eternal, to be real, that temporary things are meaningless. This assumption is worth challenging. A flower is beautiful even though it wilts. A conversation matters even though it ends. A life is meaningful even though it's finite. Temporariness doesn't negate value. Often it intensifies it. The universe's expansion toward heat death is like mortality, writ large across cosmic scales. Just as individual death gives life urgency and poignancy, cosmic mortality gives the entire universe's complexity, epoch, its special character. This isn't the end of all ends. It's the context that makes this beginning meaningful. There's also something profound about living in a time when we can still see the universe. Future civilizations, if any, exist trillions of years from now, will inhabit a cosmos where all evidence of cosmic history has been erased by expansion. They won't see distant galaxies, they won't detect the cosmic microwave background, they'll have no direct way to discover the Big Bang, to measure cosmic age, to understand their universe's past or future. They'll be epistemologically trapped in ignorance. We aren't trapped. We exist at a moment when the universe is still knowable, when evidence of cosmic history hasn't been erased, when observation and discovery are possible. We can look 13 billion years into the past by observing distant galaxies. We can measure the cosmic microwave background and see the universe as it was 380,000 years after the Big Bang. We can calculate the universe's future and understand our cosmic destiny. This is an incredible privilege, a narrow window that won't remain open forever. So what should we do with this knowledge? How should we live knowing the universe is expanding toward heat death and nothing can stop it? There's no prescribed answer because the universe doesn't care what we do. It will expand toward heat death regardless of our choices, our actions, our civilizations. Cosmic fate is independent of human will. But this independence means we're free. We're not cosmically obligated to any particular path. We can choose what matters to us, what we value, how we want to spend our brief moment of consciousness. We can explore, create, connect, discover, love, wonder. We can be curious about the universe that produced us. We can be kind to other conscious beings sharing this temporary existence. We can appreciate the extraordinary improbability and beauty of structure arising temporarily from the universe's march toward disorder. The expansion of the universe is eternal motion, a process that began at the Big Bang and will continue forever, driving the cosmos from low entropy toward maximum entropy, from connection toward isolation, from complexity toward simplicity. Nothing can stop this motion. It's woven into the fabric of space-time, guaranteed by the properties of dark energy, enforced by the laws of thermodynamics and quantum mechanics. But within this eternal motion, there are temporary eddies, structures that arise, persist briefly, and dissipate. Stars are temporary, galaxies are temporary, consciousness is temporary. Yet these temporary structures are where all meaning resides, where experience occurs, where the universe becomes aware of itself. You are one of these temporary structures. You're an arrangement of matter and energy that became conscious during the universe's brief experiment with complexity. You won't last forever. Nothing will. The universe itself, in any meaningful sense, won't last forever. It's approaching a heat death from which nothing can emerge. But right now, in this moment, you exist. You can think and feel and wonder. You can understand that the universe is expanding and will never stop. You can appreciate the cosmic context of your existence. You can find meaning in temporariness, beauty in impermanence, purpose in choice, rather than cosmic prescription. The universe is expanding, nothing can stop it. And somehow, impossibly wonderfully, that's okay. Throughout this journey, we've discovered why cosmic expansion is truly unstoppable. Not through lack of effort or technology, but through fundamental physical constraints that make halting expansion as impossible as traveling faster than light or creating perpetual motion machines. We've seen how dark energy dominates the universe's energy content and drives accelerating expansion through negative pressure that strengthens as space grows. We've explored how gravity, once thought to be expansion's eventual break, is simply too weak at cosmic scales to overcome dark energy's relentless push. We've understood how thermodynamics guarantees entropy increase, quantum mechanics forbids information destruction while allowing information fragmentation, and relativity prevents any mechanism from reversing expansion faster than expansion itself increases distances. But perhaps the most profound insight isn't about physics, it's about perspective. The universe's expansion toward heat death reveals that we live in an extraordinary moment, a brief cosmic epoch between the Big Bang's beginning and entropy's end, when complexity can exist and consciousness can emerge. This epoch won't last forever. It's already brief in cosmic terms, just a few trillion years out of an infinite future of darkness and cold. Yet here we are, Conscious beings arising from star stuff, capable of understanding the very processes that will eventually erase all trace of our existence. Think about what this means as you continue with your day after watching this. You're made of atoms forged in stellar cores, arranged through billions of years of cosmic evolution into a structure capable of thought. Your consciousness is a temporary decrease in local entropy, made possible by the enormous entropy increases happening in the sun and stars throughout the galaxy. You exist because the universe is currently in a state where such complexity is possible, where energy gradients allow brains to form and thoughts to occur. When you look up at the night sky, you're seeing photons that traveled for years, centuries, or millennia to reach your eyes. You're observing a universe in motion, galaxies receding in all directions, space itself expanding inexorably toward a future of isolation and darkness. But you're also observing a universe at its most interesting, most complex, most beautiful moment. When stars still shine, when galaxies still cluster, when consciousness can still marvel at cosmic wonders. This won't last. The galaxies you see tonight will eventually recede beyond the cosmic horizon, becoming forever unreachable. The cosmic microwave background will redshift into undetectability. The stars will exhaust their fuel. Black holes will evaporate. The universe will approach maximum entropy, a state of perfect thermodynamic equilibrium where nothing can happen, nothing can change, nothing can exist except an infinitely dilute gas of particles and radiation spreading through exponentially expanding space. But that future doesn't diminish this present, it intensifies it. You live in the golden age of cosmic complexity, the narrow window when the universe is knowable and interesting, when discovery is possible and consciousness can emerge. Future civilizations, if any exist, will look back on our era with something like envy, recognizing that we witnessed a cosmos still rich with galaxies, still illuminated by the afterglow of creation, still young enough that its origins could be discovered and understood. You are not separate from this cosmic story. You are not an observer standing outside the universe looking in. You are the universe itself, temporarily arranged into a form that can think and feel and wonder about its own nature. When you contemplate cosmic expansion, you're the cosmos contemplating itself. When you understand heat death, you're entropy understanding its own inevitable increase. When you feel wonder at the beauty of existence despite its temporariness, you're the universe marveling at its own brief experiment with complexity. This awareness doesn't have to be depressing or nihilistic. It can be liberating, even beautiful. You don't need the universe to be eternal for your life to matter. You don't need cosmic purpose to find meaning in relationships, discovery, creation, love. You exist now, conscious and capable of experience during the universe's most interesting epoch. That's not a cosmic accident. It couldn't be any other way because consciousness can only arise during epochs when complexity is possible, but it's also not cosmically guaranteed. It's remarkable, precious, and temporary. So what do you do with this knowledge? That's entirely up to you. The universe will expand toward heat death regardless of your choices. Cosmic fate is independent of human will. But that independence means you're free to create your own meaning, to decide what matters to you, to choose how you want to spend your moment of consciousness. You can explore and discover, understanding more about the cosmos that produced you. You can create beauty and meaning through art, music, writing, relationships. You can connect with other conscious beings, sharing this brief existence with empathy and kindness. You can simply experience the extraordinary fact of existence itself, that you get to be here, now, aware and alive during the universe's narrow window of complexity. The expansion of the universe is eternal and unstoppable. Dark energy will continue driving galaxies apart, accelerating forever toward maximum entropy. Nothing, no force, no technology, no imaginable mechanism can halt or reverse this process. It's as inevitable as tomorrow's sunrise, as certain as the laws of physics themselves. And somehow, impossibly, wonderfully, that's okay. Because the universe's temporariness is inseparable from its beauty, its impermanence inseparable from its meaning, you exist at the exact cosmic moment when existence is most interesting, most complex, most worthy of wonder. You get to be conscious during the universe's brief experiment with self-awareness. You get to understand, to explore, to marvel at the extraordinary improbability of your own existence. If you've made it this far through this journey, consider subscribing and giving this video a thumbs up. These deep explorations of cosmic fate and fundamental physics take enormous time to research and create, and your support makes them possible. Check out my video on what happens when black holes finally die. It explores the far future universe in even more detail, including Hawking radiation and the final fate of matter itself. I think you'll find it fascinating. Right now, at this exact moment, the galaxy closest to us is racing away at 60 kilometers per second. By tomorrow, it will be 5 million kilometers more distant. By next year, nearly 2 billion kilometers farther. Nothing can stop this, nothing can slow it down, nothing can bring it back. And somehow knowing this makes the present moment, this brief, cosmic instant when you exist and can understand your existence, infinitely more precious than if it lasted forever.